This week, in week 1, you will be reviewing something that should be a familiar topic to you from past math classes called functions. This might sound familiar, but it may not be something that you feel super confident in being able to do right now. So I wanted to do a brief video to help you kind of review what you might have already learned about functions, and if not, kind of present some material that will be important to you. So the first thing is that this is in the week 1 folder, which is found in the materials section. There are different sessions here that you'll be going through. So the video that I'm about to make here should in no way replace going through these folders. So you should still click on this Unit 1, Session 1 and work your way through the materials in there in order to understand about functions and function notation. So this video is not meant to replace those instructional things in the folders. It's really meant to support that in hopefully a brief way. I've made this video 3 times already because I've been having some technical difficulties, and it's not been as brief as I had hoped, but we'll see what we can do here. So the first thing that I want to talk with you a little bit about is what is a function. So this might be a word that you've seen before, but you may not really know what that means. So there is a mathematical definition for a function, which you will see in the week 1 materials, but I wanted to present this from a little bit more of a maybe a relatable definition. So again, this is not the mathematical definition, but it's kind of actually close, and we'll talk about that in just a minute here. So a function is a relationship. I put this in parentheses because in math there actually is a word called a relation, and technically, mathematically speaking, a function is a relation. But again, to try and make it kind of relatable, I wanted to describe it as a relationship. We'll talk about that in just a moment here. So it's a relation, or to be relatable and refer to something that you might understand a little bit better, a relationship between an input variable, we oftentimes call that input variable x, and an output variable. So that's the first part of a function. Just a mathematical relation is a connection or a relationship between an input and an output. But to be a function, it has to be a special type of relation or relationship. And in this case, that extra piece to make it a function is where each input value produces only one output value. So we're going to take a look at that in just a minute using something called a function machine. This part can be kind of confusing to kids. So I'm going to focus on this part for just a minute here when we look at our function machine. And that is that the first kind of fundamental piece of a function is that it is a relationship between an input variable and an output variable. We'll check it for this condition after we've looked at our function machine. So you may have seen or heard of function machines before. You may have seen them drawn differently. I draw mine kind of as a, well, I don't draw very well, so there's the first thing. I draw mine as kind of like a funnel input and then this kind of chute, a C-H-U-T-E kind of chute output here. So basically, we're going to plug in some values. Those are going to be our input. We're going to call that x. We're going to get out some value called y. Inside the machine, something happens to the input to turn it into the output. And so I'm going to write the equation that I'm going to be looking at for this particular example, which is y equals 2x plus 1. So basically what I'm going to do is show the relationship between my input and my output. So I can plug in lots of different numbers for x. I always like to start with really easy numbers to operate with, like 0, for example. So I'm going to plug in 0. Remember, this is 2 times x plus 1. In the order of operations, the multiplication will come before the addition. So this will be 2 times, my input is 0, so 2 times 0 plus 1 gives me an output of 1. And so what that means is that basically I can make an ordered pair out of my input and my output. So my input is x and my output is y. And I could say, well, the first ordered pair that I just discovered is that if I put in 0, I get out 1. So that is an ordered pair, or a pair of numbers that show me the relationship. that we're talking about here. So I'm going to color code the rest of these so I don't have to draw the arrows. So I'm going to plug in 1. 2 times 1 plus 1 is 3. So that gives me the ordered pair 1, 3. When I plug in 1, I get out 3. And then lastly, I'm going to plug in, I could plug in 2, but I don't have to go in numerical order like that or sequence like that. So I could plug in whatever I want. I'm going to plug in 4. So I'm going to do 2 times 4. That's 2 times my input, which is 2 times 4 is 8, plus 1 is 9. So that gives me the pairing 4, 9. So that's modeling the relationship, and a function machine shows that very visually. So I like a function machine because it kind of shows that pairing. When something goes in, something comes out. It also helps us look at this extra criteria that each input can only produce one output in order to be considered a function. So let's look at that. So when I plug in 0, there's no question about what I get out. It's not like the machine is unsure, do I get 1? Whoops. Do I get 10? Do I get 21? So when I plug in 0, there's no doubt I get out the input. There's only one, or I'm sorry, when I plug in 0, there's only one output that comes out, and that's 1. Same thing with 1. When I plug in 1, there's only one output that comes out, and that's 3. So this meets the criteria that each input that I'm plugging in only gives me one output. You will probably look at some other examples in those folders, but I wanted to show you an example of something that is a relation or a relationship, but not a function. So let's look at a function machine that does the following thing inside. So again, we're going to plug in x's, we're going to get out y's, and we are going to say that in this case, our function is y equals the square root of x. So let's remember that the square root is asking us what number times itself gives you x. So, for example, if I plug in 4 for x, that's my input, then to find the y, I'm going to do y equals the square root of 4. So now I'm being asked what number times itself gives me 4, and most kids will say 2. But the trick here is that 2 is not the only answer. There's actually another number times itself that gives you 4, and that is -2. So this input has 2 valid possible outputs. Both -2 and 2 fit this equation and make it true, which means that plugging in 4 gives me 2 different possible outputs. Well, if you think about a machine, no, we actually have very high thinking machines nowadays, but if you think about like a classic machine, like an assembly line kind of machine, when you're putting something in, the machine doesn't think, it just does. So if the machine knows what to do and only one thing comes out, we're good. But if the machine does whatever you've told it to do, and then it has to think, well, which one of these 2 things comes out? Is it 2 or is it -2? It's going to blow up. It's going to kind of like implode. And so the function will break down if 2 different numbers are possible as outputs from plugging in just one number. So that's what makes this not a function. It is a relation, or as we're calling it kind of informally, a relationship. But this is not a function because I should just type this instead of writing this. That's silly. But here I go, very slowly, at an angle even. So I really did not choose my path wisely there. But this is not a function because the input could give us 2 different outputs for that same input, and the machine's going to break down when that happens. So that's what a function is. It's a relationship between input and output values, specifically a relationship where each input has only one output. Again, you'll be looking at some more specific ways to look at that, I guess, in the materials section this week. So the next thing I wanted to talk about is a special notation that we use when we talk about functions, and not only what that notation is, but why on earth we would want to have this new notation, because it can be kind of confusing for kids. So this notation for functions is some variable, oftentimes it's an f, Sometimes it's a G or an H, but we're going to be using an F here in our example. So it's some variable and then in parentheses another variable. Now, in math, we're used to thinking of parentheses meaning multiplication, and this notation has a different kind of rule to how this works. So it's not multiplication, it's not F times X, it's actually read F of X. And basically, the kind of simple way of looking at this is that we basically, for function notation, replace the Y variable as the output with this kind of messy looking thing here. So everything else is the same. This is now representing our output. It is not multiplication. F of X is being replaced for the output Y instead of the Y. But I'm still going to go ahead and use our previous example that we were looking at, the 2x plus 1. Not every function will be 2x plus 1, obviously, but I figured we've already done the math behind this, so to save some time, we will go ahead and use that as our function notation. So basically what this does when I look at this as a mathematician or a math student is it tells me that I get my output, f of x, for my input x by doing this, 2 times the input x plus 1. So I'm going to take a moment and go to a website that kind of presents an important progression of information that might help you understand this. So let me pause here. So this is a website for this woman that is how she teaches function notation. So I kind of wanted to point out a couple of things that I saw on here. So the first thing is that you'll notice here we see our function notation. So unfortunately this pin it button pops up right in the middle of the f of x part there. So this is telling us my output when I plug x into my function f is found by doing input squared plus 3 times the input minus 1. And this notation shows me that my input is x. And I can see that I'm trying to hover over here and it's not going to work. So down here, what happens is I could replace the x with a heart. And so this tells me that for my function f, if my input is a heart, here's what I do. I do heart squared plus 3 times heart minus 1. And you'll notice that all that basically has happened here is that this input variable has been replaced by whatever this input is. So oftentimes we'll see an x there, but we could see a heart there. The next one down here uses a smiley face instead. This is an absolute value function, and I don't want to get too much into the technical component of that, but really focus on the notation part of it. So this is saying f of x is what's hidden under here. If I'm plugging x into my function f, here's what I do. I take the absolute value of x cubed minus 2x, close that absolute value, and subtract 2. If instead of x I plug in smiley face, then I do smiley face cubed minus 2 times smiley face in my absolute value signs, and I subtract 2. So we've been plugging in hearts and smiley faces. Often in math we don't do that, obviously, so we might plug in other variables. And so what we might say is, instead of f of x equals 3 times x plus 1, this is my rule. If my input is x, I could rewrite the rule in case my input is a, and I could say f of a is found, so the output, if I'm plugging in a, is found by doing 3 times a plus 1. So we might see that a little bit more commonly than hearts and smiley faces. So I'm going to bounce back to this and talk a little bit about that with our example 2x plus 1. So what I would do is this. Again, don't really use hearts and smiley faces very much in math. Sadly, no one really loves, not no one. People don't generally love or get super happy about math, so not a lot of hearts and smiley faces. Maybe frowny faces, maybe poop emojis, things like that. But anyways, what this is, we're going to use numbers instead. And so in this case, what I'm going to do is say, okay, if my rule for f is to take the input and do 2 times the input plus 1, I'm going to go ahead and plug in 0. And so instead of 2 times x plus 1, I'm going to get 2 times 0 plus 1. And that's going to give me 2 times 0 plus 1 is 1. If I instead do f of, what did I plug in up here, 1? If I do f of 1, then in place of my input, in place of x, I'm going to plug in 1, and I'm going to do 2 times 1 plus 1. So really, I'm kind of writing out a very detailed way of showing what I kind of did in my head up here, plugging my input in for the x. But I'm trying to be very deliberate about showing you the notation piece of it so that you can see that basically this notation is just showing me that this is showing my input, and I'm plugging that input in here. If it's a general rule, I might see an X or maybe an A here and here, or I could plug in numbers, and so it kind of allows me to do that. So you might understand at this point how function notation works, but you might wonder, why on earth would we ever need something like that? Why can't we just stick with X's and Y's? So before I get to that, I want to answer one other question, and that is, well, it may not be a question you have, but this is a graph of a function right here. So remember we said that the input-output relationship gives us ordered pairs, and when we plot those ordered pairs, we could get a graph. So I want to just point out the value a little bit of this notation is that even if you don't have the rule, so we have our graph over here, but I don't see what f of x is, so I don't see my general rule for plugging in x's. What do I do to the x's? But what I do see is some specific pairings. And so even though I do not see the f of x equals and what I'm doing to the x, what I do see is that when I plug in -2 into my function f, I get out 4. And so that gives me the input of -2 and the output of 4. That actually gives me the ordered pair -2, 4, which of course is hidden by my Pinterest button there, unfortunately. So let's look at another one. If I plug 0 into my function f, this is my input, that gives me an output of 3. So I should see the ordered pair 0, 3 on the graph, and I do in fact see that. So this notation shows me an input and an output even when I don't see the general equation. And so there is the usefulness of it. So here is an example to kind of put that in hopefully clearer terms. If I'm going to look at my y equals 2x plus 1. Whoops. And then I'm going to look at what is the value of writing it instead of y equals 2x plus 1. What's the value of writing it as f of x equals 2x plus 1? So let's say that I have two students, and student A and student B. And student A uses y equals 2x plus 1. So this is going to be student A. So here's student A doing their homework, and so they plug in x equals 0, and remember when we plugged that into our function machine, we got y equals 1. And then we plugged in x equals 1, and we got y equals 3. And then we plugged in x equals 4, and we got y equals 9. Okay, so we have our rule written as input and output. We have what we plugged in, we have what we got out. So let's say that student A, their dog eats some of their homework. Not all of it, just some of it. So they eat the equation. It's gone. And they eat the inputs. So inputs are gone. Outputs still exist. So now student A takes this to school the next day. And let's say the teacher says, okay, so you have the outputs there, but what did you plug in to get those? And, you know, you did the homework maybe 12 hours ago or something like that, and so you don't remember. So you're like, well, I don't know, but I have the outputs, or not you, but student A. Student A says, I don't know. I have the outputs, though, and they're 1, 3, and 9. Teacher says, okay, but that's part of the problem. I wanted to see what you plugged in. We don't have that here. So now let's look at the benefit of function notation, and then you can just ooh and ah at how amazing this is. I'm using a little bit of sarcasm there, but you can hopefully see the value. So student B says, okay, I'm going to use function notation. And so what I'm going to do is I'm going to say, I'm going to plug in 0, I'm going to plug in 1, and I'm going to plug in 4. And for my output, f of 0, so when I plug 0 into my function f in place of the x, I get 2 times 0 plus 1, which is 1. And when I plug in f of, let's see, 1. So when I plug 1 in, I get 3. And then when I plug 4 in, I get 9. So the function notation shows me not only what I got out, but it shows me what I plugged in on the other side of the equal sign, whereas y equals 1 doesn't show me that. F of 0 equals 1, when I replace this y with an f function notation, and then I plug in the input that I used to get that, which is 0, it shows me that. So now, this is dog proof. If the dog eats the homework, here goes your equation, and dog eats your input values, you still have a notation that shows you what you plugged in to get the 1, and what you plugged in to get the 3, and what you plugged in to get the 9. So, essentially, function notation is dog proof. Isn't that awesome? So as teachers, we found a way to fight the eternal, the dog ate my homework issue. So I'm, again, kind of being sarcastic, but the idea is that it does show you a pairing between input and output, and that can be helpful. So hopefully this helps to support the materials that you'll be looking at in the Week 1 folder. Please let me know what questions you have.